here. And so first, my apologies to the Zoom folks. I've elected to write on all 4 boards, so I think you'll only see the ones on the left side. So my apologies, but I think that is the best choice for me. And so the project I want to talk about today, everything I'm talking about is joint with Preston Wake and Carl Wong Erickson, and that's a lot of names to write, so I'll abbreviate this as WWE throughout my talk. Those are very important initials to me. But the project I want to talk about today is a series of 2 papers that really focuses on the relationship between arithmetic and modular forms, specifically in the setting of Eisenstein congruences. And so the main technical feature of these series of papers is an R equal T result, so a modularity result, that does not use Weil's numerical criterion. So we're really getting kind of hands-on with the arithmetic, specifically on the R side of this modularity theorem. And so we're showing an R equal T theorem. Now, I will outline that, but I'm hoping to more highlight some interesting arithmetic constructions that arise in the pursuit of this modularity theorem in a setting in which we cannot use Weil's numerical criterion. Okay, so we're going to pick up with Ribot's method, which Samit so kindly overviewed with his circle. I was hoping it would appear. And so the focus we're going to take is definitely on the bottom half of the circle. So Cuss forms, Galois representations, and then these Galois cohomology classes. They were like the bottom half of our circle. And specifically, if we could state kind of Ribot's converse to Herbert's theorem in the language coming from each of those boxes. And so I want to start just by restating Ribot's converse to Herbert theorem in the language that will motivate our exploration. So theorem due to Ribot. So we'll let P at least 3 be prime. And K is some even integer such that it's at least 4 and it's less than P minus 3, less than or equal to P minus 3. Okay, then Ribot's converse to Herbert's theorem would say in our Cuss form language that if P divides the kth Bernoulli number, which I'll denote by BK, then there exists a cuspidal Hecke eigenform, which I'll denote by F. We can write out its Fourier expansion, just as A and Qn. And we're going to say that it lives in the space of weight K modular forms for gamma 1 level P, such that for each integer n, it's not negative, we have a congruence, which we can write, so an, so the nth Fourier coefficient is congruent to the sum of divisors of n raised to the d minus k. And this congruence is holding mod some prime ideal over P in an appropriate number field that contains the Fourier coefficients of our modulus. Okay, so this is a way that we could state Ribot's converse to Herbert's theorem in the language of our Cuss forms. And in particular, I want to point out that we could pick a Hecke eigenform here of any weight that's at least 2, right? So in Ribot's actual paper, he works with Cuss forms of weight 2. I'm picking weight K here so that we actually could phrase this in terms of a congruence between a weight K Eisenstein series and a weight K Cuss form, which we can package in this language of Hecke algebras. So if I just define this Hecke algebra, so there's some Hecke action.
I mean, this is like the first third of Ribot's result, right? I mean, then he produces from the Cuss form.
Sure. So
non-zero cohomology class. And
of course.
Yeah.
So all I meant is that we could write equivalent statements at each statement.
Yeah.
That's all. Absolutely. Yeah, of course. I don't mean to say this is the whole method. I just mean
the first part, so I'm not getting the Cuss form.
Right. Like we could write down 6 equivalent statements.
Right.
And Ribot is like the accumulation of all of them.
Yes.
So we have some Hecke action on our space of weight K modular forms for gamma 1P. And so if we localize, we'll localize this ZP module at an appropriate Eisenstein ideal. And then I can rephrase this statement as saying that P divides the kth Bernoulli number implies that the ZP rank of, now we're looking at the cuspidal quotient of this Hecke algebra, is strictly greater than 0, right? So we're giving a condition for this rank of our cuspidal Hecke algebra that's picking out congruences between cusp forms of this Eisenstein series. It's positive. And so what I want to focus on today, what I mean by these ribbit method style results, is a refinement of this where we're going to look for arithmetic conditions that instead of just controlling if this rank is strictly positive, we want to be able to distinguish between a minimal case and a non-minimal case. So can we distinguish between when this rank is exactly 1 or greater than 1, or whatever the minimal rank should be in that situation? Okay. Can you all see like here when I write here? Great. All right. So now we're going to talk about some results for modular forms of weight 2 and prime level gamma naught. So some results for, so we'll look at weight 2 modular forms, level gamma naught, and is prime. And so in particular, our cuspidal Hecke algebra is acting on this space of modular forms. So you'll notice that the result, how I wrote it here, this statement, it's not going to say anything about weight 2 modular forms. And so to start, we kind of want an analog of this type of statement for weight 2. And sure enough, we have one. So a very, very famous result of Mazur in his landmark paper on the Eisenstein ideal says that the ZP rank of this cuspidal Hecke algebra is strictly greater than 0 if and only if P divides the numerator of n minus 1 over 12. And just to be safe, we'll assume that P is not n. And so this is saying that there is a cusp form of weight 2 level gamma naught n that is congruent to our Eisenstein series of level gamma naught n if and only if P divides this numerator. And so now we can talk about some refinements about when we have multiple cusp forms. So if the rank is greater than 1 of this cuspidal Hecke algebra, then we have multiple cusp forms that are showing up. And so we kind of want an analog of these conditions that will control that.
Are you assuming that n is a prime?
Yes, n prime. Correct. Okay, so the first result is a result of Morel from around 96. So this says that the ZP rank of this cuspidal Hecke algebra is strictly greater than 1. So there's extra cusp form floating around if and only if the product from I equals 1 to n minus 1 over 2, where we look at so I to the I is a pth power mod n. Okay, and so we sometimes call this, or we call this Morel's number. So this is an easy thing to check. We can just plug in these numbers and check if it's a pth power mod n, then we know that there are multiple cusp forms showing up. That's a nice result. Just to give you some other flavors, there's a result of Caligari-Emerton from around 2005. Now this we only get one implication. So this says that if the ZP rank of the Hecke algebra is not minimal, so it's strictly greater than 1, then that implies that the FP dimension of the class group, the P part of the class group when we adjoin the pth root of n, strictly greater than 1. And then a third flavor of this type of result is from Wei-Guang Erickson in 2020.
You want to just write that as n to the 1 over p. It looks funny to write.
Oh, sure.
1 over p root.
Sure. Like that?
Yeah.
Okay. Great. And so Carl and Preston show that the ZP rank of the Hecke algebra is not minimal if and only if some cup product in cohomology or vanishes in cohomology. Bless you. Okay, so I partly want to give a different, like some different flavors of the type of conditions that are related to this type of the rank over Hecke algebra. But the methods actually used the methods for 1 versus 2 and 3 are quite different. So Morel is working directly on the Hecke side of what's going on with modular symbols. And 2 and 3 instead first prove an R equal T theorem and then leverage that to get information here about the class group of this extension and here this cup product vanishing. If you're not familiar with R equal T theorems, there's just some universal object that's associated to our deformation, Argawa representations. And there's this Hecke algebra that should be parametrizing our modular forms with the correct conditions. And so when I say R equal T theorem, I mean that the data of those two objects matches in a natural way. Okay. And so the result of Carl and of Wei-Kwang Erickson is the closest to what I want to talk about today. So I just want to briefly kind of run through a sketch of how this argument is working. So sorry, Harvey, going to the other board. All right. All right, so to prove 3, Wei-Kwang Erickson, they study a deformation ring, which we'll denote by R. So Galois pseudo representations. Pseudo deformations of, and then we're going to let rho bar be equal to 1 plus our cyclotomic character. So this is our mod P cyclotomic. Okay, and so there's some set of local conditions that set up our deformation problem. I'm going to sweep those under the rug for now. I'll talk about it more precisely when I go to the setting I will focus on for our work. But so there's some set of local conditions that allow us to construct our R. And so for this proof of 3, kind of the starting step is to construct R, which is highly non-trivial. So I felt bad giving it step 0, but that's how it is in my head. So construct R and prove R equal T via Weil's numerical criterion. And so again, since we're in the residually reducible case, it's tricky no matter when, but the construction and dealing with R is quite nuanced. And so once we have this R equal T, the second step is to ask, well, what's the tangent space of R? So specifically, we want our maps from R into the ring of dual numbers over Fp. Okay, and so Carl and Preston show that in this setting, there's one tangent vector, which will denote R1 when it has the shape. So we have our cyclotomic character times 1 plus epsilon. We have a log function, which is picking a map from Fn across to Fp. And then here we have the Kummer cocycle attached to our prime L. And then we have another cocycle that's uniquely defined because of the fact that P divides n-1. So we have the shape. And so beyond showing that the tangent space of R is one-dimensional, Carl and Preston show that.
So yes.
Yeah.
How do you know that it looks like from what you've written that it's reducible mod epsilon squared? right, I mean, like somehow, it's not just mod epsilon is at 1 plus W, but what am I trying to say? Like the determinant is just W. Sorry, and what am I trying to say? I mean, somehow I'm surprised that there's epsilons on both the B and the C coordinate, rather
So-
than just one of them. That's what I'm asking.
So I think perhaps, I'm not sure if this is what you're asking. I'm writing it this way carefully because I'm writing it as matrix homomorphism instead of something into a GMA. So we would like, if you're thinking about it in terms of a,
I mean, I'm sure it's correct. I'm just like usually you don't necessarily know that like both the B and the C are 0 mod the maximal ideal, just one of them is, right? So you have your B coordinate and your C coordinate have
Right.
epsilons in them. So that's what I'm asking about. How do you know that it looks like that?
They prove it in their paper.
Oh, they prove it.
part of the content, yeah.
Right in the local conditions and.
Okay, okay, yeah, okay. So it's just
Yeah, it's
something,
not trivial.
it's not sure, okay. Okay.
Okay. So in particular, once we have that this is our one-dimensional, this is our unique tangent vector, then they also show, which is again non-trivial, that that this will deform mod epsilon cubed exactly when the size of R is at least 2. Okay, so the question for the last step, when can row 1 be deformed to a second order? Okay, and so they show that row 2 exists if and only if the cup product be cup C equals 0 in H2, if and only if the rank of R is strictly greater than 2. And so this is the cup product that I'm talking about here. And so I want to highlight before we go on is that there are 2 directions of the statement coming from, if we think about it in terms of this ribbit circle, right? There's the statement that if we have a larger rank of R or T, they're equal, that we get a statement about the existence of a Galois extension with very specific local conditions. And so that direction kind of comes from this machinery that we're talking about with Ribot's method. The other direction, where if you have a Galois extension with specified local conditions, that it really is coming from a modular form, that you do not get from this, and you really need some sort of R equal T argument to go in the direction. Okay, so I'll say this while I erase because I'm already running a little behind. But so this method that I've outlined very briefly, it generalizes to other settings beyond prime level. Specifically, Carl and Preston tackle a number of square free level cases, but the key point that one of the key points that I want to make today is that their previous work for the project I'm talking about, it really somehow relies on being able to invoke Weil's numerical criterion. So you need R and T to have some nice geometric properties. And so the goal now, or the point of the project that I'm talking about, was to somehow take the worst or the best possible case in which this approach is not going to work and try to handle that through explicit computations on the R side. Okay. All right, so what's the setting I want to consider? As I said, it's a very specific setting. And the reason it's so specific is just because, as you'll see, the arithmetic gets unwieldy quickly. So this is just the smallest setting that we could handle. So our setup, and I'll refer to it as Ribot's new form setting. The reason why will become clear in a moment. All right. So with P at least 5, we're going to fix the following notation. So first we fix the prime L naught. We want it to be congruent to 1 mod P. And this is to guarantee from Mazur's result that there is a cusp form of weight 2 and what will be level n. So n with L1, L2. That's all. Right, so this guarantees that we have a form of level L naught that satisfies an Eisenstein congruence. But to keep our arithmetic in check for now, we also want to assume that the ZP rank of our Hecke algebra of level L naught is exactly 1. So we could check that using Morel's number or your favorite method. And this condition is one that is most likely like we could relax fairly straightforwardly. But again, we want to keep our arithmetic in check for now. And then our second prime, we do not want it to be plus or minus 1, 1p. But we do want L1 to be,
So what does T sub L1 mean again?
it's just the Hecke algebra when we're looking at it acting on the space of forms of level L naught.
Level, okay.
So we're, yeah, we're just saying there's a unique Cuss form of level L naught. Okay, so L1 is a p power mod L naught. And so if you look carefully at the Mazur paper on the Eisenstein ideal, you'll recognize that this condition is what Mazur calls a bad prime. So we want L1 to be a bad prime mod L naught. And you'll see why in a moment. Okay, and so since our level has 2 prime divisors now, that means we have 3 Eisenstein series, or our Eisenstein space has dimension 3. So to single one out, we're going to let E sub 2 n with this decoration epsilon be the weight 2 Eisenstein series of level gamma naught n with Akin-Lehner signature, which I'll denote AL, signature -1, -1. So each prime L naught and L1, we're specifying that we want the Akin-Lehner sign to be -1, -1. So that singles out a unique Eisenstein series. So this is a setting that we're going to consider. And the point is that under these assumptions, the rank of our modular Hecke algebra is at least 3. So why is it at least 3? Well, we have, can't spill. So we have our Eisenstein series. We have our form of level L naught, and then this condition, the Mazur bad, this actually gives a new form level n with an Eisenstein congruence. And so this might be surprising if you've thought like a little bit about Eisenstein congruences, but not a lot, because this condition is not increasing the p-adic valuation of the constant term of this Eisenstein series, but the existence of this new form is due to Ribet. So that's why we call it the Ribet new form setting. The third one is due to Ribet. Okay, and we can check computationally. Bless you. That T is not LCI, not a local complete intersection ring. And so this is the setting that we want to explore with try to develop a new way to show R equal T. And so the starting point is that in Wake-Wang-Erickson's, in the square-free paper, where they handle the cases using the strategy that they're able to, they still, so from Wake-Wang-Erickson, we have a surjection from R onto T. So in this setting, it's Wake-Wang-Erickson still handle setting up the deformation problem, constructing our R, and giving it the map from R onto T. And so the idea is that we want arithmetic conditions that guarantee that R will be as small as possible. And that's going to force an isomorphism for R equal T. So in what I say, we're going to be missing the other direction, right? We're only going to get R equal T when R is small, and that forces T to be small. Now, I just want to point out very briefly that, of course, the goal is to show that the R constructed by Wake-Wang-Erickson is always the correct R for square-free level. This is just the first kind of test case to see if we could get it to work. Yes, okay. All right.
So what does it mean to construct R? Like, how did they construct it?
I really just mean that the setting up the deformation problem. So in this setting, I'm about to kind of talk more about it, but it was introducing like the unramified or Steinberg condition. That corresponds to the fact that we want square free level here. And so the idea is that moralistically, that condition should really match for any square free level. Yeah. Okay.
So but if you took T0 here, is it an LCI? Is it just the two
It's-
cos forms
Yeah,
intersecting transversely? Okay.
Yeah, that causes. We can write down, maybe at the end, if I don't think I'll have time, but afterwards I can write down, like you can write down pretty explicit presentations for mod P, what's going on. Like that, so when we're checking that this is not LCI, we're,
Right, but I'm just saying T0, like where you look at just the cos forms.
oh, sorry, can you repeat your question?
Oh, I was asking if T0 is an LCI.
Yeah, I believe that it's still not, yeah.
Oh, it's still not.
I might be getting confused because in,
Okay, sorry, I'll let you.
yeah. I'm getting a little confused because I'm revisiting some of these settings with using U operators instead of Akin-Lehner, and then like nothing is well behaved. So
whether that's LCI or not, it would be very difficult to do an R equals D theorem just for the hospital.
Yeah.
Okay, it
algebra.
would be difficult.
Yeah.
I see. Okay.
okay, so henceforth, I'm gonna have to go a little faster. Going very quickly. So henceforth, we're gonna fix a triple P L naught L1, P L naught L1, satisfying Ribot's new form setting. So just the setting that I just wrote above, we're just gonna assume we have it fixed. And so following Wei-Kwong Erickson, we're going to again study this R that is capturing deformations of this same row bar. And so I'll just say them out loud. So now this is what Sam was asking about, the conditions that should correspond to this problem. There are 4. So we want the local conditions of R, we want our pseudo representations to be unramified outside of NP. We have the determinant is cyclotomic, and that corresponds to the fact that we're dealing with weight 2. Then there's a finite flat condition at P, and then the unramified or Steinberg condition that I was mentioning corresponds to the fact that we want to work with gamma, level gamma, not N. Okay, and so our situation is much more complicated than this because we first show that there are two tangent directions, right? So we have our good old row 1 as before, but now we have this row 1 new. And so the notation's a little heavy at the beginning, but then hopefully I'll convince you that it's not too bad. Okay. I'm going to write it and then I'll explain what I'm writing. Okay, so this is the form of it. And so as before, I'm trying to write this carefully as a matrix homomorphism. So this is going from GQ into FP epsilon mod epsilon squared. And so when we look at this, so first we just immediately ignored this. I just wrote it to be precise, but since we're only tracking the determinant and trace, we can just ignore what's here. And so these 2 co-cycles, they correspond to the input that we have from this problem, which is L naught and L1. So this corresponds to L1. This is our Kummer, a choice of a Kummer class corresponding to L1. And then this comes from the fact that L naught minus 1 is divisible by P. So this is kind of like the input of this machinery. And then D1 is just chosen so that our row 1 new has the correct determinant. And so really the data, or what I want you to take away from row 1, so the data of row 1 new, is really this cochain A1 and it satisfies a boundary condition such that, so we just have and this we can just get from chasing our homomorphism property, right? Like if we want this to behave like a homomorphism, then we need a choice of, we need A1 to satisfy this boundary condition. And it exists because L1 was bad, according to Mazur, right? So because L1 is bad, this product will vanish in cohomology, and so we can find such an A1. So we're happy. And so similar to the prime level case, what we prove is that the FP dimension of R mod PR is not minimal, so it's at least 4, if and only if rho 1 nu deforms to a second order. First order, yeah. So it deforms to some rho 2 nu. Okay. And so now our question is, well, what's the shape of rho 2 nu? So when is it going to deform? And so the much more complicated to write down all of the like boundary equations that we need to be satisfied for the second order deformation. So I'm just going to boil it down to the important bit. So the data of this rho 2 nu is the following. So we get another cochain, which will denote B2. And it also needs to satisfy a boundary equation. It's a bit more complicated. Nothing that we can't write down. Great. Okay. So now, unlike the case with A1, it's not clear a priori if there's a solution to this type of boundary equation or to the specific one. And so now we need to check some local conditions. So rho 2 nu is going to exist if and only if our cochain A1 on the previous board vanishes at Frobenius at L1. This is a nice local condition at L1. So if this condition is met, then we can write down a rho 2 nu that makes sense. And then we want to know, basically, we have to check that it will satisfy all the local conditions, but the one that's sticky is it Steinberg at L naught? And this will happen if and only if this weird invariant that we call alpha squared plus beta also vanishes. And so we can think of this as a local condition at L naught. So the alpha and beta, they're associated, like alpha comes from a local condition on A1 at L naught, and beta comes from applying a local condition for B2 at L naught, and then we want to check if it vanishes. Okay, so I'll refer to these as like our two invariants. And so the main technical output from this, I guess it appears in the first paper. Right, is that the FP dimension of R mod PR is not minimal if only both of these invariants. So the invariants in 1 and 2 both vanish. Okay, and then as I said, we get this corollary that if either invariant does not vanish, then we conclude that R is equal to T, and both have ZP rank 3. So to go from a statement when we're working mod P to a statement over ZP, then it's an application of Nakayama's lemma. And so it makes sense in our setup that we only kind of get one direction because we don't have R equal T at the start. So we're only getting equality when one of these variants does not vanish. So I'll talk about this a little bit at the end, but I just want to mention now that computationally, we have found that this first condition is always satisfied. And so that's something that I'm working on currently, work in progress, to show that that actually is true, like from a theory point of view. And so really, it's this alpha squared plus beta invariant that's controlling this minimality condition in this setting. All right, so I'm finishing around 45 or 40.
50.
Okay. Great. Okay. All right, so this is the main technical output, and now I want to try to reinterpret. This is part of the talk I like more. I want to try to reinterpret this in terms of algebraic number theory, so in terms of some much nicer language. And in particular, and actually, I'm going to switch to a board that our Zoom audience can see. And so the kind of magic for the rest of the talk is really theory. And so just for ease of notation, I'm going to restrict this whole discussion to our Galois group, to the Galois group where we're fixing Q zeta P. And so really I'm dropping the twisted. And this again, it just means that when I'm writing down various matrix representations, I'm going to drop the omegas from the discussion. Okay, so to start the discussion, we want to consider a representation given by the following shape. So we have B1, C1 star. And so we're viewing this as a map from GQ zeta P into, so we have our unipotent degree 3 matrices over F3, and we're quotienting it by the center. By the center, like so. And so basically, we're just forgetting what's in the top right entry of this map. Okay. All right, and so the point is that liftings to U3, well, they exactly correspond to solutions A1 candidate that satisfy the boundary equation that we wrote before. Okay. So again, these are the same cocycles that we fixed earlier. And so the candidate subscript now is just to emphasize that I've dropped local conditions. So I'm just talking about kind of the Galois aspects of the picture. And so anytime that we have a solution here, we plug it in here, that's going to give us a lifting to U3, which will then cut out a degree 3 extension of Q zeta P. Okay. All right, and then similarly, I'm going to try to fit it here. So we have 1, let me be careful. So we have 1, 0, 0, 0, 1. So now we want to play this game again. This is okay, and so now we similarly fix a representation, a matrix homomorphism now into U4 over FP, again pushing by the center here. And so now this one's a little bit harder to see. And so the way we should think about this is actually a choice of 2 overlapping. I hope I did this right. 1, 2.
Can I ask your U sub n is what?
Unipotent.
Unipotent. Oh, okay.
Yeah, unipotent. Yeah. So we should think of this 4x4 matrix as actually being overlapping 2 3x3, which I've outlined. So we have the orange where we have B1 and C1 on the off diagonal, and then we have C1, B1 on the off diagonal in the bottom. And so if we view it that way, then it turns out that lifts to U4 exactly correspond now, you might guess, to solutions of our other boundary equation.
Are you looking at 3 now? Just sure.
Oh, no, so sorry. I'm working mod P. It's funny, I asked myself that a moment ago and I was like, 3 looks good. No, I mean, so sorry, thank you.
There's a few more.
Okay, I'm working on,
Yeah.
I'm so sorry.
Okay.
I think I got confused because this is
3, yeah.
genuine 3 and then I kept going. Where are the other ones I'm missing?
Just they're lifting.
Oh, thank you. Sorry about that. Thank you. Okay. So this was a little, I think this one is, I think you would buy if you've studied, you know, these types of cup products at all. This one's a little trickier to see. So this is actually an instance of a triple Massey product, which is more nuanced to set up. And so in particular, I'm saying instance because in order to write down a triple Massey product, we first need to pick a defining system. And so that basically constitutes the information here, where we have to make our choice for the cochains that are kind of solving the 2 overlapping. Okay, and so we could say that this is an instance of a triple Massey product with defining system A1 and D1. So we've made those choices. Great. Okay, and so I'll stay over here for Zoom. Okay, so yeah, erase, I have boundary. Okay, great. Okay, and so now we can make a really nice little diagram for ourselves. Right, okay, and I was going to write the triple Massey product this is related to, we could write as B1, 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 which we're reading off our off diagonal here. Okay, so diagrammatically, what do we have? Well, we have Q, can you all see here? Yeah. And then we have Q zeta P. Okay, and so then we have what I call K and L. Oh no. I'll fit it. And they're composite, which I just call M. Okay, so what's K? So K is cut out by B1. So it's coming from, it's just adjoining the P root of L1. And then L1 is coming from C1. And then we said that via this correspondence, a choice of A1 canned is going to cut out this extension M prime. And then, sorry for running out of room. Imagine this going straight up again. We have B2 can cuts out another P extension M double prime. And we can give nice characterizations of these M prime, M double prime, reading off the local conditions on our various cochains. So if I'm not going to write them, I'll just say them out loud. But for example, so M is just defined once we fix L naught and L1. M prime is, so it's Gawa over Q with our specified Gawa group. It needs to have a certain Gawa action of Q zeta P over Q. So it should be trivial. It's unramified everywhere. And it should be L naught split, which I just mean that all the primes of L naught here should split in M prime. And then there's a similar set of conditions that will cut out M double prime. And so now we can revisit our main theorem, which I didn't erase. Great. Okay. So for condition 1, the following are equivalent. So we have that our cochain, that's just that for Frobenius, FL1. So that's our original condition. So this corresponds to M prime over M being what I am calling L1 split. So it just means that all the primes in M, they split over L1, they split in M prime. And this is the same as saying that M double prime over M prime has degree P. Because remember, we said that a priori this B2 need not exist. So this is the condition that controls that. And then for condition 2, Now I'm going to assume one holds. Then the following are equivalent. And we can make statements if one doesn't hold, it just, you have to be a little more careful. So we have this alpha squared plus beta vanishes, where we can say that the conjugacy class of the decomposition group at L naught that sits inside our Galois group of M double prime over Q at order P. And I'll just say the last one since I'm running out of board space. But basically combining this one with the fact that M double prime over M prime has order P, we could just turn this around in terms of the order of the normalizer of this decomposition group, if we wanted it in that language. And so we basically can reformulate the main theorem in any of these languages. And I usually present it more in the number theoretic way. I think it reads nicer. Yeah. But our the corollary will still hold. Like the point is like, if the normalizer of the decomposition group has the right size, then we'll get an R equal to Q.
So what kind of extensions of Q are you getting here?
So we're getting, so in terms of degree, every line on the board except this one is a degree P extension. And so we call them like twisted Heisenberg or generalized twisted Heisenberg. So this is like a true twisted Heisenberg extension. And then this like, I think is not technically a Heisenberg extension, but we call it that because it's, you'll see it in a moment coming from like Sharif. Okay, so in my last few minutes, I want to talk about this question of how do we generate these fields that we want to find, right? So they're cut off these properties, but our goal all along was to actually check if these conditions hold, right? Like the point of this project is to actually check what is going on. We want to check on the R side and we want to check on the T side and we want to see that they match. And so it turns out that these fields are quite big, at least for a poor coder like myself. And so we actually, to do the computations, want to restrict down to K. So I'm going to redraw our diagram, restricting down to K. Great. So we'll end with computational aspects. Ooh, I think I'm on 4 now. Okay, and so if we redraw this picture, then what we have is, so we have Q coming up to Q zeta P, and then we have K, which is still cut out by B1, and now we have K prime and K double prime. K prime is cut out by B1, and K double prime is cut out by B2. Now, a big difference between these two diagrams is that K prime and K double prime are not defined canonically. They depend on choices, like we have to choose a prime over L naught, these types of things. These M prime and double prime are defined canonically. And so the point is that
Prime and M double prime are abelian over K, right? Or not?
I
think if B1, if I set it to 0, then it's just
they're abelian, I think, over Q zeta P. I don't think they're abelian all the way down to Q.
no over K. I was just saying.
K. Oh yeah.
Yeah.
Okay, so the point of the computational aspects is to really find an explicit S unit that generates the extensions K prime and K double prime, because then we can actually verify these computations just using computations in K plus Kummer theory. And in particular, this one will just correspond to like K prime over K is L1 split. And then this second condition, it actually just means that we can find 1 prime in K over L naught that splits simultaneously in our 2 extensions. That's what it's corresponding to. And so you might think, okay, well, what are we going to do? I tried Sam's approach of just looking and looking and looking. Didn't work very well. And so our goal is to find this A1 when we restrict K, B2. And we want to think of them as, so we're thinking them as being in class. And we use the Kummer isomorphism. So we want to find S units here that correspond to these extensions or these these cochains. And so what's really nice is actually that Sharifi's theory gives formulas. So Sharifi's theory gives a formula directly for our A1 situation, and then we have to do a little bit of playing around with Massey products. So just to illustrate, so we just need 2, so to compute the candidate solutions. So by this, I just mean we're forgetting local conditions here. Well, we need to fix 2 elements. So we need to fix a C inside Q zeta P, P, such that we can write L as Q adjoint theta P. That way. Right, so we're just fixing a Kummer generator for L, and then we need to fix some gamma that lives in K. This, such that the norm, when we take it from K down to Q zeta P, is equal to the C. So I kind of think in my head, if you have your K and your L, that we're somehow like intertwining these 2 extensions. And then Sharifi's theory gives some really nice formulas. So the first formula, we have that A1 candidate. Restricted, of course. K candidate. We can write this as just the first order Coley-Vaughan derivative operator applied to gamma. That's all. And so a formula for the ith Coley-Vaughan derivative operator, we can just write down quickly. J equals 1. Great. And our group ring, where G is just our Galois group of K over QP. So I usually don't write out the formulas, but I think it's nice given the context. And part of the point is like, this is extremely implementable and computable, right? As soon as we've set the problem up correctly, like computed RC, computed various other S units, then we're basically just applying a very clean operator to that. And then I won't write the formula for B2 out just because it's a bit longer, but I'll just say it uses the second order derivative, plus there has to be some component after you nail down your A1, right? So there's some dependency between these choices. And so we view this problem, this is just step 1. We view this like finding these S units in 2 steps. So first, we want to compute the candidate solutions that just satisfy the boundary equations and therefore satisfy the Galois conditions. And then our second step are to make our local adjustments coming from the local conditions that I mentioned at the beginning. And so what I was saying before is that to go from A1 candidate to actual A1, you have to make an adjustment, and then that's going to impact the formula for B2. And then I'll say for B2 that Sharifi's theory handles or gives a nice formula if you were to reverse the order of these 2. So there's a special type of Massey product that's a cyclic Massey product. So if it instead looked like B1, B1, C1, then we would get a straight up formula. It does not. And so instead, we just have to do some Massey product magic. But yeah, the punchline is that we can compute these S units. The local adjustments were kind of the most annoying things to compute. And then basically, we computed these in a range of examples with P equal 5 and P equal 7. And in all of the settings, in all of our computations, we found that condition 1 holds. We found that condition 2 holds if and only if the rank of T is independently computed to be non-minimal. So at least 4 using modular symbols. So that's kind of like good evidence that what we're saying is correct. And so I'll just end with a few closing remarks, which is really about this annoying condition 1. So it's been fairly annoying for a long time, where computationally we had noticed that this condition is always satisfied. And we actually checked that condition much farther out because it's an easier computation to check. And in fact, like in this whole diagram, you could also check it on the L side, and then that's a bit easier. But Carl and Preston, I could not find a reason why this was vanishing. And so in this project that I'm co-leading with Carl and Alice, where we have kind of developed the theory for R, for the pseudo-deformations, for level gamma 1. And kind of the nuance there is that you have to use the U operators, not the W operators. And so we're hopeful, it's like pre-work in progress. We're just like hopeful that this, more than hopeful, but less than in progress, that this is going to allow us to show that this, in fact, does always vanish. And so then in our analog, it really is like this alpha squared plus beta that's controlling the minimal rank. So I will stop there.